First, what is motivation to do quantum gravity? So these days, if you want to do something concrete, if you have a lot of energy, you are a good student, then typically you choose different subject. You go and do particle physics, especially apply particle physics in cosmology, and you have a lot of work. So quantum gravity is only for those people who still want to dip deeper. On the other hand, not having really any urgent reasons for this, as it will be pointed out at the next transparency. Nonetheless, there is some motivation. To begin with, Einstein himself, even though he was known as a person who was not enthusiastic about the quantum theory, nonetheless, even he himself admitted that gravity should have some quantum version. Well, also Richard Feynman, who also himself, I think, wrote the first paper on quantum gravity, which actually was not written personally by him. He just gave a lecture in Jabłonna in '62, and then the organizers of this lecture wrote a paper according to the recording of his lecture. So I wish my papers were published in this way. That would be really helpful, because I don't like writing papers. And he also at least implicitly encourages people to do something which is not standard and what not everybody is working on. Loop quantum gravity quantum gravity is a subject for which, as I said, we don't have really there is no emergency. We don't have any numbers which we should be able to explain by fundamental theory. On the other hand, you might think that given this lack of constraints, there should be many works, many different approaches to quantum gravity. On the other hand, there are not that many. So you can probably list them easily. I listed below some main approaches which I know. So it means that each of those approaches is solving some conceptual, some structural constraints, and each of those approaches is worth knowing about. There is a so-called asymptotically safe quantum Einstein gravity. It has something to do with the renormalization group, with path integrals. This is not what I'm working on, but there are quite solid results in this approach. There is non-commutative geometry approach. Here in Kraków and at this conference we have Professor Heller and Professor Sitash. There is string theory, very famous. There is loop quantum gravity, I will be speaking about in this lecture. And here in Kraków there is a young researcher, Jakub Mielczarek, who is working on this. There are also discrete models called dynamical triangulations, and here in Kraków there is also a strong center of research led by Jerzy Jurkiewicz. So my talk is about loop quantum gravity. I would like to report some results. However, before this I will start with quite general passage through simpler theories than quantum gravity. Namely, there are two approaches to quantum theory. One approach is to try to build quantum theory from scratch as a fundamental theory. Like, for example, you can see in the book by Weinberg this construction of quantum of Hilbert space of one particle states, then quantum operators are constructed by using the representation theory, etc., without reference to classical physics at all. On the other hand, there is another approach called quantization, which uses some extra structure which we know from classical theory to guess the form of potentials which we add to free Hamiltonian, or to guess the form of generators of symmetries. So we shouldn't consider classical theory as fundamental, and quantization as some exact procedure. This is only a way of guessing some correct theory at the end. So loop quantum gravity also relies on this strategy, on strategy of guessing theory from classical theory. So let me first briefly pass through quantum physics to emphasize some points which later are also emerge as in quantum gravity, either as solved or also as unsolved. So let us start just with quantum mechanics. So what about quantum mechanics? Here everything is simple. We have observables, positions, and momenta. We have we know what is p squared. We know what is potential depending on q. We have Hamiltonian. States are some functions belonging square integrable, and with the help of those functions we calculate expectation we define expectation values of our observables. However, if you for instance take some function, some generic function of q and p defined on classical phase space, and you ask what is the corresponding quantum operator, then you find that actually there is ambiguity. So if we take function q times p squared, we can quantize it in this way, but we can quantize it also in this way, or we can quantize it in many inequivalent ways. So the conclusion is that quantum theory, even in such simple case, doesn't give us a unique answer for what is quantum operator corresponding to such function, and we need some physical input, physical input to define such operator. So you can guess that in quantization, this is one of the difficulties which we address. Now, what about relativistic particles? So consider, so actually. Oh, sorry, it's not massless. I forgot to remove this word. This is a massive quantum particle. So actually, a relativistic particle has a lot of properties very similar to canonical gravity. So this particle can be described by 4 degrees of freedom, 4 positions, 3 regular positions and 1 time considered also as position, and the corresponding momenta. However, there is an extra constraint. This is the constraint. And now, according to theory to the framework with constraints derived by Dirac, physical observables should commute with the constraints. So here we have beautiful algebra of commuting of functions or operators commuting with these constraints. This algebra, they generate the Poincare algebra. So we can choose this algebra of observables, and now we can conclude that the quantum theory is defined in a Hilbert space, which is representation of this Poincare algebra, such that the momentum conjugate to time is positive, and such that this identity is satisfied. And also in this case we don't encounter spin, so also spin should be 0. So this gives us, so quantization immediately gives us this statement that one particle Hilbert space should be a representation of the Poincare algebra, which is starting point for quantum field theory for quantum fields and quantum states of free quantum field theories in flat spacetime. However, if we ask about position operator, okay, as long as we are in the classical theory, then we can easily find Dirac observable which commutes with the constraint and which corresponds to time at a given, to position at a given instant of time. However, if we would want to construct corresponding operator, then we encounter ambiguity, because here we want to turn into an operator some algebraic expression which involves if we replaced P and T by operators, it involves operators which don't commute. So it's not uniquely defined. We have to make some choice. Then we have to make sure that this choice satisfies some Lorentz covariance. And then we have a lot of problems. So even in those easy cases, we encounter some problems. Now if we go on to quantum field theory, then we see that, briefly speaking, in quantum field theory, observables are fields at point of space and time. So they are fields at point of space-time or at event. The key calculation of quantum field theory is calculation of this expression, which is integral with respect to the positions of time-ordered product of potentials describing interaction, and this product is sandwiched, or we consider its expectation value with respect to some final and initial state, and we want to assign uniquely a number to this. So then we write it in terms of Feynman diagrams. Then we discover that some of them are infinite. Then we introduce renormalizability of theories and non-renormalizability, and so on and so forth. However, even in this theory, we discover some phenomena which are confusing. Namely, if you want to consider a vector field which has properties of, mathematically properties of for potential of electromagnetic field, then it's easy to see that there is no well-defined quantum free operator corresponding to this field. A quantum field operator corresponding, having this, the properties, algebraic properties of this field, is actually defined modulo such transformations, up to such transformations, which should be considered gauge transformations, which means that the physical content is independent on them. Okay, so we can conclude fine. So instead of A, we know what to do. We just take F mu nu, and F mu nu is unobservable. Okay, this is a good solution. However, nature prefers to use A. So those actions which we use in quantum field theory, they involve A. We have this coupling between electromagnetic field and other fields, usually in terms of A times potential rather than in terms of F mu nu itself. So even though we would prefer to use F mu nu, we have to use A, which is not really uniquely defined. If we apply the same arguments just based on theory of representations, this is pure theory of representations of the Poincaré group, to an operator whose index structure is the same as that of gravitational field, and it's massless, then it turns out that in similar way as electromagnetic for potential, this operator can be defined only up to such transformations where this is the famous, the well-known form, infinitesimal form of the action of diffeomorphisms on gravitational vector field, on gravitational field, on the metric tensor. And again, nature prefers, still insists on using this operator, which is not really well defined, because in the coupling of matter with other fields, we find G mu nu as this, the coupling, explicitly G mu nu coupled to other fields. Okay, finally, let us consider for a moment quantum field theory in curved spacetime. So when we consider quantum field theory in curved spacetime, then actually we are forced to reformulate the quantum field theory. Namely, a quantum state is given just by assigning, you may say assigning by hand to every product of the field operators in question some number. So this number can be called endpoint function. And those endpoint functions have to satisfy suitable algebraic conditions to define uniquely a state. In curved spacetime, vacuum is not unique. There is no uniquely defined vacuum. We can define something vacuum-like states from a symmetric part of one of those functions, of two-point function, and then assuming that theory satisfies so-called Wick theorem. Then by assuming this Wick theorem and by fixing the symmetric part of the two-point function, we can reconstruct the vacuum state, and we can reconstruct by the GNS construction, which was mentioned by Professor Sitash. We can reconstruct the Hilbert space, the Fock-Hilbert space, and the representation of those operators. However, different vacua lead to, in general, to inequivalent Fock spaces. And even if they define an equivalent Fock space, then still the notion of particle is not well defined, because the creation and annihilation operators are also not uniquely defined. They depend on this notion of vacuum. Further on, time evolution is just given by any choice of coordinates. So we know that in general relativity there are many choices of coordinates. Each choice of coordinates can lead to the following equation, and if there exists in this Hilbert space an operator which satisfies this right-hand side, then we can call this operator Hamiltonian. However, in general, this operator is not well defined. So in case of curved spacetime, we actually have to understand better what it means, whether different inequivalent Hilbert spaces mean inequivalent physics, and whether it means that only one of them is correct and we need to know more, or whether it means that all of them somehow give rise to some physics, but this physics is not defined in a unique Hilbert space, but in all those Hilbert spaces. I think this question is not really completely agreed. I mean, the possible answers to this question are not agreed about by all the physicists. Okay, so after this short passage through the best known part of physics, let us move on to gravity. So gravity is a theory with constraints, and the constraints in gravity actually generate transformations which actively move space-time. So to explain this, let us recall this original Einstein's argument. So suppose we know solution G mu nu to Einstein's equations in this region below the dark line. And even to make it more, this geometry, to materialize this geometry, let us consider a particle which is moving, and geometry is telling this particle what its trajectory should be. Still, the extension of this geometry beyond this line is not unique. So suppose that this orange G mu nu is an extension which satisfies the Einstein equations, then this particle would go on along this extension of its trajectory. However, there are infinitely many inequivalent G mu nus, which also satisfy the Einstein equations with this initial condition. And if we choose any of them, then the particle will go this way. So if we pick some point x0 of this bare manifold, and if we ask, is this particle going to pass through this point, then we can see that gauge transformations can change our answer. For some choice of G mu nu, this particle really passes through this point, but for other choices, it doesn't pass. So the notion of a point of a manifold is actually not well-defined physical concept. What is well-defined is when we consider two particles, one here and one here, and suppose that for some solution, for some extension of g mu nu to a solution in the complete space, those two trajectories intersect. Then the fact that they intersect is gauge invariant, and also which means that if we choose different gauge equivalent g mu nu's, then the particles again intersect in a different point of the manifold, but actually their intersection is what we physically mean by a point. So when we physically think of a point of space-time, in fact we don't mean a point on a manifold, we just mean this intersection of two material particles. So actually it's good news for every physicist, because physicists don't want to know what are differentiable manifolds. On the other hand, for mathematicians who think that differentiable manifolds, they solve all the problems of general relativity, the message is that actually they are on fundamental level, they are useless. So this manifold structure is some auxiliary structure, but we have to learn how to get rid of it, or perhaps how to formulate gravity in such a way that we even don't invoke this structure at all. I'm not sure that anybody has done it thus far. Okay, so what are we looking for when we quantize gravity, when we look for quantum gravity? So, as I explained, fields, the gravitational field or some matter field at the space-time point xt is not an observable. So this is something we are not used to. We are used to using fields, and we think of them as some observables. In case of matter coupled to gravity, g mu nu at xt, or even this matter field at xt, is not physical observable because point is not physical. So what is physical? So what I'm going to tell you is, so what is physical is some relations, is relations between given fields. So for example, let us fix first 4 classical fields. Suppose that they are not degenerate, so they can be used to form coordinates in space-time. Then relation of the 5th field with those first 4 is an observable, as well as the relation of any other of those fields. So we can say, let us take the first 4 fields to be coordinates, and then physical degrees of freedom are given by the remaining n-4 fields, written by using the implicit function theorem as functions of the first 4 fields. Classically, it doesn't change, this observation doesn't change anything, because classically we are allowed to use any way to parameterize a given solution or space of solutions. However, if we quantize a theory, then depending on what we fix as those reference, which fields we fix as those reference fields, we will obtain a different quantum theory. So the shape of our quantum theory depends on this choice. Okay, and this choice can, given a choice, we can introduce more physical terms. Namely, if we promote one of those fields to time, we'll say that let phi 4 be a time coordinate. Then changes in this phi 4 will be considered time evolution. And then we can even calculate derivative with respect to this kind of change. And if this derivative, if we have quantum representation for those, so if we quantize this dependence of those, if we quantize those relational observables, we have quantum operators, and if we calculate derivative with respect to t, and if this can be written in this way, and if this H can be given a meaning of joint operator, then we will say that in this way we defined effective physical Hamiltonian. So here a lot depends on the choice of those reference fields. And there are two possibilities. Either we should understand quantum theory of general relativity such that nothing depends on this choice, what is true in the classical case, or it means that there is some more structure which physics provides, quantum physics, in suitable choice of those fields. So let me briefly tell you about the literature. So those observables which I told you about is an example of so-called relational Dirac observables. So relational observables are regular Dirac observables, however special ones. And they were described by Rovelli in his books. They were also described by other authors. And this specific construction from the previous transparency actually is called deparametrization. And perhaps there are some older papers, I don't know, but the oldest which I found was by Kijowski and Smulski, in which perfect fluid was used as to deparameterize gravity. There were also later papers by Rovelli, Smolin, by Braun and Kuchar. So I will, in the next transparency, I will tell you a bit more about this last example of using dust to define space-time, because this example is perfect from the point of view, from the mathematical point of view. It's using, in this example, you can easily understand what is the idea behind this creating space-time by using some material fields as a reference coordinate system. So consider gravity coupled to dust. So it turns out that dust can be actually described by 4 scalar fields. So you can introduce dust without using the word dust. You can introduce 4 scalar fields, and here I didn't write explicitly suitable action, but there exists such action. And then if you solve the classical equations, then you will find that actually every value of S1, S2, S3 defines uniquely a geodesic. So we can think of this geodesic as geodesic along which particles of dust, some particle of dust moves. And the 4th field T, according to the field equations, becomes the proper time along this geodesic defined by any choice of values for S1, S2, S3. So indeed, those 4 scalar fields coupled to gravity, they define system which has all the properties of dust coupled to gravity. This dust comes with some mass parameter which I didn't here explicitly write. So now what is quantum theory of such system? So this theory was sketched by Braun and Kuchar, who didn't have quantum Hilbert spaces and quantum operators. So they did it on so-called formal level. So they assume that all the operators which they need exist just by putting hats. So this procedure is sometimes called hatization. They put hats upon fields, and then they say, okay, let it be operator which satisfies all the properties which I need. So on this formal level, they conclude the following, that quantum state is a functional which depends on gravity and on one of those 4 dust fields. However, gravitational field is represented by coefficients of g mu nu calculated in the coordinate system defined by the dust fields, which means take for x mu, take S1, S2, S3, and T, write coordinates of G mu nu in this in these coordinates, and then use them as independent fields, as independent variables. The scalar product is some scalar product which doesn't depend on T, which depends only on G mu nu, which is like formally defined integral, functional integral with respect to G. So T plays the role of time, because it just gives some. So element of Hilbert space is psi at any instant of T, and as T changes, then this element changes. Those Dirac observables, they have this form. So every Dirac observable is given by some component of the metric tensor, which is evolves like in Heisenberg picture with respect to certain operator, certain which we identify as, which we call effective Hamiltonian, times T, which and in this way the theory takes appearance of theory defined in just in space of dust. So in this way, dust degrees of freedom are swallowed by gravity. Solving the 4 constraints of gravitational field, we just swallow the degrees of freedom of the dust. Dust becomes, I mean, those dust fields become just coordinates. And what is quantized is gravitational field defined on this space of dust. So what was missing in this example were actually quantum Hilbert spaces and quantum operators. So now the
very quick question. The dust is nevertheless physical in that it's acting back on the geometry.
In what sense?
Dust is physical in the sense it's not a test field.
Right. No, it's gravitating dust. It's gravitating dust. Yeah. Right. So what quantum gravity provides is exactly those missing Hilbert spaces and missing operators. Loop quantum gravity provides quantum states, Hilbert spaces, and quantum operators, which we can use to actually give meaning to the expressions from the previous transparency. And in this way, we define the first quantizable model of gravity. So in this sense, gravity coupled to dust was the first model of canonical gravity coupled to something, to some matter, which is completely quantizable. This was done by Tiemann and Giesel, and you can complete this construction and give explicitly Hilbert space, Hamiltonian operator, and observables. I'm not saying that the outcome is very easy to understand. These operators are technically very difficult, so it's very difficult to sit down and just do any simple calculation. However, they are precisely and exactly defined. A second model of this form, similar to this, was defined by replacing the dust by a massless scalar field. So those of you who know cosmological models obtained by symmetry reduction, which use massless scalar field and gravity symmetry reduced to homogeneous spaces, they will understand that the second example is generalization of symmetry-reduced cosmological models to actually cosmological models with all the degrees of freedom. However, here we were able to do it only for massless scalar field. This is important that this scalar field is massless. And a third model, which has those properties, is sort of a combination of the first two, which has properties similar to the first one and to the second one. It was obtained by Pawłowski and Hussain by considering non-rotating gas. In the first dust. In the first case, dust is rotating. In the second case, dust is non-rotating. So now, how much time do I have? Okay. So let us see how much I can tell you in 5 minutes. So let me tell you what is this loop quantum gravity, which actually is doing, so which provides us with those quantum Hilbert spaces. So in loop quantum gravity, gravitational degrees of freedom are expressed by a SU2 connection and canonically conjugate momentum. So mathematically, this is the same phase space as a phase space of Yang-Mills SU2 theory. However, equations are different. And then there we have some matter fields and lapse and shift functions. And this theory is subject to the gravitational constraints. So there is scalar constraint, there are three components of the vector constraint. Additionally, there is Gauss constraint, but this is not Yang-Mills Gauss constraint. This is gravitational Gauss constraint corresponding to rotations of this frame. There are possible other constraints coming from the other degrees of freedom of the matter fields. And all of what I wrote here, it is valid for four-dimensional spacetime. However, there are now generalizations to bigger dimensions than 4. Now, loop quantum gravity, okay, but I should also say that that those Yang-Mills-like variables, they encode gravity in the following way. So connection, this SU2 connection consists of the Levi-Civita connection and of the extrinsic curvature with some fixed parameter. So given gamma and so given orthonormal frame and extrinsic curvature, these are formulae which you use to construct this those variables A and D, and vice versa. You can use this to calculate E and K. And loop quantum gravity, just very, very briefly speaking, it amounts to considering variables which are parallel transports along all possible finite curves of this connection A, and fluxes with respect to all possible two surfaces of this variable E. And the advantage is that the Poisson bracket of that those variables close to Poisson algebra without infinities, without delta functions. So Poisson bracket is a constant times A. And now for this algebra, we find quantum representation. Actually, we prove there is a unique diffeomorphism invariant state defined on this algebra. From this state, we have representation which we identify with some diffeomorphism invariant measure defined on some Gelfand spectrum of this commutative subalgebra of this algebra, which is Gelfand completion of the space of connections. On this, here we have this measure. And this space can be decomposed into, there is orthogonal decomposition into finite dimensional subspaces labeled by graphs, whose links are labeled by irreducible representations of SU2. And if we further more consider Gauss constraint, then we find that here at the nodes of those graphs, they are admissible only invariants of this tensor product, and the result is sort of generalization of the Penrose's spin networks, which were also mentioned today in one of the talks. So, because my time is over, let me go to the summary. So the summary is, so you can very often hear this phrase that there is no quantum gravity. So of course we don't have theory which we know that is tested and which satisfies, which is confirmed by observations. However, we have quantizable models for which there exists explicit proposals for quantum theory. This theory, so for the time being, we have only simplest models given by coupling gravity to simplest types of matter. However, there is no conceptual obstacle which would enable us to generalize those models to actually all the standard fields of standard model. With the existing models, we can at least qualitatively describe the Big Bang and gravitational collapse. It means that classically they admit Big Bang solutions and gravitational collapse. And finally, there is this final question. So suppose that we consider seriously all the matter fields coupled to gravity, then according to what we learned, 4 degrees of freedom are swallowed by gravity. So what about the Higgs field? Higgs field exactly consists of 4 scalar fields. So what if we swallow those, if we choose those fields to be swallowed by gravity, and what is the outcome of such theory? So actually nobody has done this on technical level, so we can only wonder what would be the result. There are also other conceptual questions, but if nobody asks, I don't have to raise them. So it's a good point to finish. Thank you.
Any questions, please?
I mean, the Higgs field, I mean, is of sort of different nature. I mean, you have gauge transformation of the Higgs field, but how can you swallow it to gravity?
Okay, so an open question is how can we combine 2 different techniques? So we have one sort of techniques which are used in the standard model. So we have the spontaneous symmetry breaking, we have Goldstone fields, we use Higgs field to give mass to some other fields, etc. On the other hand, in gravity, we have another type of techniques which are familiar for canonical relativists, which is swallowing field degrees of freedom by solving Einstein equations. And now the question is whether those 2 groups of techniques can be made compatible, or if they exclude each other, but both of them rely on existing equations. So in some sense, we should consider we should find a consistent way of understanding application of 2 kinds of arguing, of two types of argumentation.
If I might just short second question, the topology of the, so say, 3-dimensional space you take is flat, so it's trivial.
So actually, mathematically, ideal topology for this consideration when everything is well defined is compact 3-dimensional space times R. For instance, S3 times R, because then we don't have those boundary degrees of freedom and boundary conditions. If we want to consider, for instance, asymptotically flat spacetimes, then it is this notion of asymptotic flatness is very difficult to understand. So I at least don't understand the quantum structure of asymptotically flat infinity.
Could you say something about something? I keep meaning to try and really understand loop quantum gravity, particularly as Lee Smolin makes me out to be one of the godfathers of this theory. But what I'd like to understand is exactly the role of the bare manifold. I mean, Rogers spin networks were defined just as purely combinatorial things, but my understanding is that the bare manifold is still playing an important role because of the way the spin network is embedded in the bare manifold.
Right.
Is that right? And would you say that that's a certain concern about loop quantum gravity. It's claimed that it's background independent, but it seems to me it's rather dependent upon a particularly ghostly bare manifold. Is that a very unfair comment?
So this is one of the technical, not technical, actually conceptual problems which I mentioned, but I didn't really define. So according to this procedure, which I'm sort of person which refers to exact results. So exact result which I'm presenting is that we start with manifold, background manifold. On this manifold we have gravitational field and other fields, and we introduce some quantization procedure which leads us to definitions of operators and Hilbert spaces. However, it's true that this procedure relies on some given manifold, and the idea is that what we should quantize is we should quantize gravitational field and other matter fields defined on a manifold. On the other hand, you are right that once we see the outcome of this, we can also speculate that perhaps that manifold is not necessary. Maybe it's easy to... So what I defined here actually still knows about this manifold, because those states are defined as embedded graphs. But we can easily remove this manifold by considering only abstract graphs. And actually, with some small effort, we can modify those definitions such that they are well defined for abstract graphs. And then we can say that there was no manifold, that there were only abstract graphs, and that this manifold maybe should be found in some semi-classical limit. However, technical details are not completely obvious. In this case, with three dust fields, what people do, what the authors do, Tiemann and Giesel, they show that actually this time evolution, this Hamiltonian, should preserve every graph. So if every graph is preserved individually and is independent, so if during evolution those graphs don't talk to each other, then natural assumption is let us throw away all the graphs but one, and let us assume that it means that somehow there is some sort of spontaneous symmetry breaking, or some super selection rule applies, and all the physics is defined only on one abstract graph. And this graph is abstract. It doesn't know about any background structure. In case of gravity coupled, in case of some other quantizations, we cannot do it as easily. However, the short answer is that among all possible definitions of quantum theory which can be obtained in this way, there is a subset of definitions which don't require this background manifold.
Yeah, if I could just follow that up, is that an aspiration rather than a proof? I mean, it seems as if you're going back to Roger's original desire that everything should be defined in terms of graphs and combinatorics. My question is, are we ever really going to recover general relativity in that thing? I think this is what Lee Smolin calls the inverse problem. And I have to say, when I look at these various attempts to derive space from graphs, and I did quite a bit of thinking about this with Lee 23 years ago, Lee is very convinced that space, that the foundation of things is discrete. And I have to say, I came to the conclusion that was just trying to get too much out of too little, what I already said earlier today. Maybe not much will come out of not much. That's my concern, whether one can do it with that. So I have to say, just at the moment, I feel it's an aspiration rather than a result.
So aspiration is the semi-classical limit. This is your
well, has one even got that?
Comment. Yes, so this is a question, whether semi-classical is, whether given just a theory on a single graph, whether we can reconstruct, by using by defining some limit, whether we can reconstruct the manifold. I agree with you that I haven't seen such construction. So there are some works on semi-classical limit, but they are only partial. They give only partial results. I don't see systematic construction of emergent manifold and classical gravity from this. So this understanding of the semi-classical limit is still an open question, as far as I'm concerned. Maybe somebody else could tell you, be more optimistic.
Thank you.